Hi everyone. So in this video, I will be introducing graphs to you. This is the first video in the graph series, and here I will be talking about the definition of the graph, the properties, and the terminology that is used when we're talking about graphs. So this session will act as a base for the next subsequent sessions in which I'll be talking about the algorithms which are used for the graphs. So let's begin. So in computer science, data structures can be classified into two categories: linear data structure and non-linear data structure. So linear data structures can be arrays, linked list, queue, or stack. And in nonlinear data structures, mainly there are two categories: tree and graph. So graph is one of the most important data structures because it is an important part of the interviews of the lateral hires. And also, if someone wants to test your data structure knowledge, he will most probably ask you a question about graphs. And I've seen a lot of students face many issues in solving problems related to this topic. So I thought that maybe I should clarify this topic and go into depth layer by layer. So in the first layer, I'll be introducing to you what are graphs all about and what are all the terminologies that you should be clear about. So the first question comes, what is a graph? So as we discussed earlier, graph is a non-linear data structure. So it basically comprises of two parts. So it has a finite set of vertices and a set of edges that connect them. So in the diagram, I have shown a graph. So it has five vertices: A, B, C, D, and E. So the vertices are also known as nodes. And you can see a lines connecting each of these vertices. So this line is called an edge. So if you see any graph problem, you will see that it has a finite set of nodes and a finite set of edges. So the nodes are basically where we store the data. So here in this graph, the data is of the form character. So A, C, B, these are all as characters. So it can be of numerical data type also, or any other data structure, that doesn't matter. So basically in the vertices we store the data and we have set of edges that connect them. So this is the basic definition that we can use to describe a graph. So now an important question arises, that why are we studying the graph? What are the basic applications of a graph? So I can give you some real life examples that where graphs are used. If we take an example of the Facebook, so we have users. So users are basically considered as the vertices. So if there are two users, let's say user A is there and user B is there. So if they are friends, then there will be an edge connecting them. So based on this, Facebook stores all the data related to friends, and then it can suggest to friend suggestion algorithm of Facebook also works on this concept. So it checks that the user you are friends with. So what are the users that they are mutual friends, and based on that, it can give you suggestions. So the algorithm is quite complicated, but the basic idea that they have used, the basic data structure they have used is graphs. So second example that we can take is World Wide Web. So that is basically our internet. So let's say you open any site. Let's say you open the Economic Times. You see various news on it. You click on a news, it opens a new page. So this link to a new page can be considered as a edge. And when the new page opens, that is a data. So that is can be considered as a vertex. So web pages are considered to be vertices, and if there is an edge from page A to page B, then we can see that page A has link of page B. So the third example that we can think of is Google Maps. So we all have used Google Maps. So it is are in our phones, in car navigation systems, everywhere. So Google Maps, when you type a destination, it tries to find the shortest destination, shortest time that it takes to reach the destination. So it uses the graph algorithm to determine that shortest route. So what it thinks is, so let's say we have this road. So we have a crossroad. So basically this is considered as a vertex. And these are the roads, so these can be considered as edges. So there are various algorithms in graphs that can be used to determine the shortest route from point A to point B. So Google Maps used those algorithms to find the shortest route when you type a destination. And another application that we can think of is flight networks. Let's say a flight wants to travel from Delhi to, let's say, a long distance, let's say Los Angeles. Then usually the flights don't carry that much fuel, so they have to stop at some airport, then they reach the destination. So then they have to find the shortest route that they can take to reach the destination so that the fuel cost is less and subsequently the ticket cost is also less. So what the flight networks do, they store the data in the graph and then they find the shortest path and the fuel that can be used for the route planning. So graphs are used for the route planning mechanism in the flight networks. So next we have product recommendations. So when we shop on e-commerce websites like Flipkart, Amazon, and all these websites, so when you buy a product, you see some other recommendations. So let's say you have bought face cream and it will suggest some other products which have been bought by other users. So how Amazon or these sites work is they store these data in a form of graph. So let's say if a user A has bought some products and if a user B buys one of these products, then it is more likely to buy the other products also. So to find this mapping, so they have used the graph data structures. So these are some of the most common uses that we can find of the graphs. Also, there are many more uses which we will subsequently find when we discuss the other algorithms. But just to give you a real life examples where graph can be used. When we are talking about graphs, if you read some books or you come across some problems, you will come across these terminologies that are used here: connected graph, disconnected graph, directed, weighted, cyclic, acyclic, simple graph. So these can be pretty confusing if you don't know what are the definitions or what is meant by when you say undirected graph, what is meant by when you say sparse graph. So here I will try to break down all of these topics one by one with some examples, and then it will clarify that what is meant when someone says it is a disconnected graph or a directed acyclic graph. Let's begin with the first one. We have the connected and disconnected graph. So it says that graph is said to be connected if there exists at least one path between every pair of vertices. So if we take the first example, let's say you want to reach point E. So the node E can be reached from D, D can be reached from C, C can be reached from A or B, B can be reached from A or C. So there exists a path between each pair of vertices. So if you want to traverse from, you are at point A and you want to reach point E, then there exists a path. You can go from A to C, C to D, and D to E. Similarly, from B to D, you can go from B to C and C to D. So this graph is known as a connected graph because from any point you can reach any other point. There exists at least one path. And if we take another example, so I have removed one edge from here. So now we have this graph. So if someone says to you, you are at point A and you have to reach point E. So there is no way that you can reach point E or point D from point A because there is no edge that is connecting them. So this is known as a disconnected graph. So basically a disconnected graph can be a combination of two or more connected graphs. And these individual connected graphs, these are known as components. So this disconnected graph is comprised of two connected graphs or two components. So next we come across this terminology a lot, which is directed graph and undirected graph. So in the previous example, when we say that you have to reach from point A to point E, so there is no direction here. You can see that this is a straight line. So you can traverse from A to C and you can traverse from C to A also because there is no direction. So graph is called as undirected graph because there is no direction order, traversal order that is defined. But if you see here, there is an arrow pointed. So what this arrow means is that you can reach A point from C. So C to A is possible, but A to C is not possible. So if someone tries to do this, this is not possible. Similarly, A to B you can reach, B to A is not possible. So B to C. So this arrow determines the direction order that you can take. So in a directed graph, each edge has a direction which determines the traversal order. So in a graph, either all edges are directed, or there is no direction in each of the edges. You cannot have a mix of both. Like some edges have direction and some have don't. So that is not possible. So if you see this, here we can traverse in any order C to D or D to C, but here you can only traverse from C to D. So this is an important concept that you need to understand, that what is difference between directed and undirected graph. So next we come across weighted graphs. So in the early examples we have seen that this edge has no weight associated to it. So what do you mean by weight? So basically weight can be thought of as cost. So if you have to reach, so let's say you have to reach from Delhi to Chandigarh. So the cost can be the fuel consumption or the toll amount that is taken. So similarly in computer terminology, if you have to reach from point A to point B, you have to incur cost of 2. So these are the numerical weights that are associated to each edge. So if you have to reach from point A to C, you have to incur 5 cost. B to C, you have to incur 2 cost. B to D, you have to incur 4 cost. C to D, 5. D to E2, E to C, 5. So now where it can be useful. So you can think of, let's say, these are the different cities. So you can think of, let's say, A is Delhi, B is Chandigarh, and you can think of E is, let's say, Gujarat. So if someone tells you what is the least cost effective way to go from point A to E, so let's say from Delhi to Gujarat, how can you go? So how can this problem be solved? So one method can be you can find what are the possible ways of reaching from Delhi to Gujarat, what are the different routes that are available. You compute the distance between each of the routes, then you compare the toll cost, and all these you compute, and then you find which is the minimum that comes up. So these two, 5 and 5, this can be, let's say, considered as kilometers. So from Delhi to Chandigarh, let's say 300 kilometers is there. So instead of 2, you can write 300. So 300 will be the cost from traveling from Delhi to Chandigarh. And this C, let's say this is Noida. From Delhi to Noida, if you have to go, you have to incur 5 cost. So in this way, you can compute the cost that is required to travel from Delhi to Gujarat. And if you compute all of these costs, you can find what is the minimum cost that you have to incur from reaching from point A to some other point. So the weighted graphs are useful there when you know what is the cost incurred to reach from a vertex to a other vertex. So the cyclic and acyclic graph. So let's have this first graph. So this is a directed graph as we discussed earlier. So from C you can reach A to B and B to C. You see there's a cycle formed here. From A you can go to B, B to C and C to A. So if there is a graph that contains at least one graph cycle, then that graph is contains a cyclic. That graph means a cyclic graph. But if a cyclic graph possesses only one cycle, then it is called a unicyclic graph. And what is a acyclic graph? So acyclic graph is a graph that is not cyclic. So acyclic graph is a very common terminology that you'll find. So it is also known as DAG. So DAG means directed acyclic graph. So here you can see from C you can traverse to A, from A to B. So from B you cannot go anywhere. So to reach B you have to go from C. So there is no cycle because you can go only till here and then it ends here. But here from C to A to B and B to C. So you can see there is a cycle. This is a cyclic graph, this is a acyclic graph. So you'll come across many graph problems where they'll say that let's say you are given a graph, you have to find that if there is a cycle or not. So an important property of a cycle is that it starts and ends at the same point. So here you can see a cycle starts at C, it goes to A to B and B to C. So the starting and the ending point of this cycle is C. So there are many ways to find out if the graph has a cycle or not. So that I will be discussing in the next video. So here my aim is to get you familiar with all the graph terminology that can be used. Next is a dense and a sparse graph. So dense graph is a graph in which the number of edges is close to the maximum number of edges. So this is a example of a dense graph. We have 5 vertices, we have maximum of 10 edges. Here, so this is a example of a sparse graph. We have only 5 edges. So sparse graph is a graph in which the number of edges is close to the minimal number of edges. So there is no exact definition, but it's just to give an idea. When someone says it's a dense graph, then the social network graphs can be seen as a sparse graph, because a social, let's say Facebook has millions of users, but each user will have only limited number of friends. So that will be a sparse graph because the user let's say 100 or 200 friends, but there are millions of users in the entire Facebook. So that graph will be a sparse graph. Then we have a simple complete graph. So this is very confusing. Sometimes people confuse what is a simple graph and what is a complete graph. So a simple graph is a graph which is without loops and without multiple edges. So what is meant by multiple edges? So multiple edges means that, let's say, from point E and D we have only one edge. But if we have, let's say, another edge, and this edge has a cost 2 and this edge has a cost 1, then these are multiple edges. But if it then that this graph is not a simple graph. A simple graph is a graph which has no loops and no multiple edges between two nodes. And a complete graph is a graph in which each pair of distinct vertices is connected by unique edge. So can you tell me which one of these is a simple graph and which one is a complete graph? Okay, so this one is a simple graph and this one is a complete graph. See, the difference between this is, so point D and C there is no edge connecting them, and here we have an edge connecting each of the unique pair of vertices. So we have vertex A, B, C, D and E. So any unique vertices there is an edge connecting them, but here there is no edge connecting D and C. So this one is an example of a simple graph and this one is an example of a complete graph. Okay, so next comes strongly connected graph. So a graph is called strongly connected if there exists a path from a node A to node B in each direction. So what I meant here is that, let's say you want to go from point A to point B. We can see there is a path. But if you want to go from point B to point A, we can see that we have this path. Similarly, for D to A, we have this path. And from A to D, we can go here, then go here. For D to C, we have this. And from C to D, we can go like this to this. So we can see for any node U, if there is a path from U to V, then there should be a path from V to U. So this should happen for all U and V. So if such a scenario is happening, then that graph is called a strongly connected graph. So next comes these important terminologies that you need to understand for a graph. So I've divided them into 5 types. So one is adjacency, in degree. So this will be comprised of in degree and out degree. So I will explain them to you. Then is path, cycle and walk. So let's start with what is adjacency. So when we talk about adjacency, then we should know whether we are talking about vertices or edges. So this graph, it has both adjacent vertices and adjacent edges. So adjacent vertices are those vertices which have an edge connecting them. So if someone says which are the adjacent vertices in this graph, so we can see there's an edge from A to B. So A and B, AF, so these are adjacent vertices. So B and F are adjacent vertices of A, B and F are adjacent vertices of E, E and C are for D, E and C are for B. And similarly, adjacent edges are if there is a common vertex between the two edges. So the example can be AB and BE, for AB and BE. So the common vertex is B. So these are the adjacent edges. So next I have written AF and FE, AF and FE. So this is the common vertex. So if there is a common vertex, then those edges are adjacent. If there is a common edge, then those vertices are adjacent. Next is degree. So when we talk about degree, so degree term is used for a vertex. So it is the number of vertices that are incident, number of edges that are incident on a vertex. So as you know, for directed graph, there is no concept of direction. So the number of edges that are connected to a graph that are connected to a vertex, that is known as the degree of that vertex. For directed graph, we can split it up into in degree and out degree. In degree is for incoming edges and out degree is for the outgoing edges from a particular vertex. So let's take an example. So let's say you have this graph. So we have to compute in degree and out degree for each vertex. So let's compute in degree. What is the in degree for the vertex E? We can see there is no arrow pointing inwards to vertex E. So the in degree is 0. For D, we have one edge that is incident, that is incoming towards D, that is E to D. So we have it is 1. For C, we have 2. For B, we have 3. For A, we have 1. So this is the in degree. And what is the out degree? So the out degree for E is out degree for D, out degree for C, out degree for B, out degree for A is 1. So for each vertex we have computed the in degree and out degree of the vertex. So it is very simple, you just have to check the number of the arrows that are incoming and outgoing. So pick any vertex, check the number of arrows that are incoming towards it, that will be the in degree, and check the number of vertices which are outgoing, that will be the out degree. And the degree will be addition of the in degree and out degree. So degree of vertex A is 1 plus 1, that is 2. Degree of vertex B is 3 plus 1. Degree of C is 0 plus 2. So that is how you compute in degree and out degree in a directed graph and degree in a undirected graph. So then there is a common theorem that says that sum of in degree and out degree is even in graph. So why do we say that? So if you see, so each edge is computed twice, considered twice. So this edge is considered as an out degree for vertex E and as in degree for vertex D. So as each edge comprises of in degree and out degree also. So simply it is a multiple of 2. So we can say that it will be even. So sum of in degree and out degree will be even for a graph. So next comes path, cycle and walk. So this is very commonly used in all the graphs problem, but there's a confusion, slight confusion between all of them. So I've tried to list them all in a single slide, and then we can discuss what are path, what is a cycle, and what is a walk. So basically, a path is a sequence of distinct vertices such that the vertices are adjacent. So if there is an edge connecting the two vertices, that can be considered in a path, but the vertex cannot repeat, so it has to be distinct. If the path is closed, then it is a cycle. So if the where the path start, if it ends at the same point, then it is a cycle. So basically, and what is a walk? A walk is a sequence of vertices and edges. So there is no condition here that the vertices or edges cannot be repeated. It is simply a traversal of the graph. So let's discuss this with an example. So we have this graph A, B, C, D, E. So it is an undirected graph. So let's find out what can be the path. So the path can be, let's say if we go from A, we go to D, from D we go to C, from C we go to B, and from B we go to E. So you can see we went only across the edges. So we went only the check the vertices which are adjacent to A. We pick D, from D to C, C to B, B to E. So this is one path. So there can be other path also. Let me check other path. So from A we can go to B, from B we can go to C, from C we can go to D, and D we can go to E. So this can be another path. So there can be many paths. It's just that the vertex should not repeat. And what can we cycle? So cycle is when the starting and the ending is same. So if we start from A, B, C, D, E, and we end at the same point, then it is a cycle because we started and the ended at the same point. And what is a walk? So let's say a walk can be, let me choose a different color. So walk can be you go from A to B, B to C, C to D, D to E, E to B, B to C, C to D. So we are just traversing across the graph. So it does not matter whether the edges are repeated or the vertices are repeated. So I hope it is clear. So this was all about graph introduction. Please share your feedback and suggestions in the comment box below. If you like my content, do like, share, and subscribe to my channel. I will soon be back with the next video in this series. Until then, this is Sandeep Thapar signing off.